Dear students, welcome and thank you for tuning to another video. We are still talking about phase diagrams in the material science course. In this video, I'm going to explain the effect of temperature and composition on the material that we are creating or processing and manufacturing, and how the phase diagram will help us in identifying and understanding the effect of temperature and composition. If you remember from the beginning, the first video, we said that in order to understand material properties, especially if there's an alloy or a mixture of two or more elements, we need to look at the temperature, the composition, and the pressure. We're going to assume that the pressure is the same in all cases. We'd like to see the effect of temperature and composition. And when we say composition, what is the concentration of each element inside my mixture? Solutions means that it's one phase, but mixtures is multiple phases, if you remember from the previous videos. We look at this diagram here. I have this my phase diagram, and we're going to use again the water and sugar phase diagram. The y-axis is the temperature and the x-axis is the concentration. At zero concentration, this means that I have 100% water and zero sugar. You see that the composition is percent weight of sugar on the x-axis, which means that all the concentration here are just sugar. So this is 100% water, zero sugar. This is 20% sugar, 80% water, 60% water, and 40% sugar. And at the end of the line, we have 100% sugar and zero water. Now, if we started from point A, let's say that I have a mixture, and my mixture is at 20 degrees Celsius, and it has water and sugar, and the concentration, the components, we have 70% sugar and 30% water. So I will be in this location. If you look at the phase diagram, from the phase diagram, we know that under these conditions of temperature and composition, assuming the pressure is the same, under these conditions, my mixture is going to have two phases, one liquid and one solid. So I'm in this region to the right of this solubility curve, right? So if I increase the temperature, if I heated the solution, let's say from 20 degrees Celsius to 100 degrees Celsius here, it means that I crossed the solubility limit, assuming I still have 70% sugar and 30% water. If you increase the temperature, we are moving up here. So now I am to the left of the solubility curve, which means that I have only one phase, which is just the liquid. I can also change the structure or the material and its property by changing the composition. So let's say that from B at 100 degrees Celsius, instead of having 70% sugar and 30% water, I've added 20 more percent of my solution to be sugar. So now I am 90% sugar and 10% water. If I am at the same temperature, I'm going to move back into the liquid and solid state, which means the two-phase state. I hope this diagram explains the importance of the phase diagrams. Also, this video and this slide shows the importance of phase diagrams. So you can say that if I have a mixture of 70% sugar and 30% water, you want it to be in a liquid state, just raise the temperature. If you are at 100 degrees Celsius and it's one phase and you want it to be two phases, increase the concentration of sugar and then you go to the two phases. So that's how we use the phase diagram. This is a very simple schematic and explanation. Now, this is the simplest phase diagram. We're going to look at much more complex phase diagrams, but we are trying to explain things step by step. Before I finish this video, I want to highlight one more point, is that there is a criteria for solid solubility, and the criteria is that you need to have two elements and they need to be as similar to each other as possible. And if you remember from our previous lecture, sorry, it's imperfections, not imperfections. Yes, that's the right thing. So in the imperfections lecture, I talked about something called Hum-Rothery. Sorry, I'm modifying the slide on the fly. No, never mind. So the Hum-Rothery rules that you need to have your elements have the same crystal structure, face-centered cube, and that's the case with nickel and copper. And also they need to be very close in electronegativity, 1.9 and 1.8, and the radius of the atoms is very close, 0.1246 and 0.178, which means that nickel and copper, they can be, they can totally, they're totally soluble in one another for all proportions from 0%, let's say nickel and 100% copper to 100% copper and 0% nickel. And that's why we're going to use this example over and over in our next slides and videos. But if you want to revise and look back to the Hume-Ruther rules, please go back and look into the imperfections lectures, and you will get more information about what does that mean. Now, at the end of this video, I hope that we know the effect of temperature and composition on our material and our mixture, and also what are the criteria for solid solubility. They have to have the same crystal structure, very close in electronegativity, and they have the same dimensions. Now, here's what happened. If we are not within that range, so if we have two elements that they're very different in their crystalline structure and electronegativity and the radius, we're not going to have a mixture anymore. What we're going to end up with is one, let's say, block of material, but within that same block, I have nickel alone and, let's say, copper alone, if they are different in their crystallinity, electronegativity, and radius. So it's no more a mixture. We can't say that they are homogeneous. And the atoms, you'll find the nickel atoms alone and the copper atoms alone, and you will have like pockets of nickel and pockets of copper inside your block. And this is not an alloy or a mixture anymore. I just wanted to highlight that. I hope that is clear. Thank you for watching. Until next time.